Hello everyone, we will continue our discussion on conic sections. In particular, we will study about ellipse and hyperbola in this lecture and the next. So, in the last lecture we discussed about equation of tangent, normal etcetera to an ellipse. This lecture will continue first with ellipse. So, first thing we will derive is formula for equation of chord of contact of tangents from an external point x 1 y 1 to an ellipse. So, consider the ellipse x square by a square plus y square by b square equal to 1, and let x 1 y 1 be a point outside the ellipse. So, we have this ellipse and we have some point x 1 y 1 which lies outside the ellipse. Now, from this point x 1 y 1, two tangents can be drawn to the ellipse, and what we are required is to find the chord of contact. So, let P be this point and Q and R be the points on the ellipse where the tangents are drawn, and then we want to find the equation of this chord Q R. So, let this is say point P, suppose P Q and P R are the two tangents where Q and R lie on the ellipse. So, let Q be the point x prime y prime and R be the point x double prime y double prime on the ellipse. Then the equation of the tangent line. So, recall equation of tangent at some point x prime y prime is given by x prime by a square plus y prime by b square equal to 1. So, therefore, this in this case will be the equation of line P Q, and similarly equation of line P R is x double dash by a square plus y double dash by b square equal to 1. So, these are the equation of the line P q and P r. Now, since the point P x 1 y 1 lies on both P q and P r, we have. So, if we put x 1 y 1 in this equation for P q, then we get x dash x 1 by a square plus y dash y 1 by b square equal to 1, and x double dash x 1 by a square plus y double dash y 1 by b square, this is also equal to 1. So, we get these two equations 1 and 2. What we had to find? We had to find the equation of the line q r. So, we need equation of the chord q r. So, notice that q and r, these are the points x dash y dash and x double dash y double dash. So, if we have any straight line on which these 2 points lie, then that will be the equation of the straight line q r. So, consider the equation x times x 1 by a square plus y times y 1 by b square equal to 1. This is equation of a straight line. Note that 1 and 2 implies, so 1 implies point q, which is x dash y dash, lies on the above line, and 2 implies the point r, whose coordinates are x double dash y double dash, this also lies on the same line. Now, there is a unique straight line passing through any 2 points. Therefore, this equation is nothing but equation of the line joining q and r. So, since there is a unique straight line passing through two distinct points, the equation is of the line joining q and r. Thus, what we get is that equation of q r is x x 1 by a square plus y y 1 by b square equal to 1. So, note that this equation looks very similar to the equation of the tangent line at point x 1 y 1. but in this case the point x 1 y 1 lies outside the ellipse. So, we have this ellipse and we have any point x 1 y 1, and then the equation of the chord joining this 2 point q and r is nothing by plugging in x 1 y 1 in the equation of the tangent line at a point on the ellipse. This gives us the formula for the equation of the chord. Next, we will do this problem, prove that the normal at any point on the ellipse bisects the angle between the lines to the foci. So, let us draw a diagram. We have an ellipse and suppose there is a point P. So, we have there are two foci, let us call them F 1 and F 2, and suppose we take any point P on the ellipse and then we look at the line joining the foci to this point P. What we have to prove is that the normal at this point P, this is the normal line, this bisects the angle this. So, to show the normal at P bisects angle F 1 P F 2. So, what we will do is let us look at this ellipse and let us look at the point P and the two foci F 1 and F 2. And here is okay. So, let us look at the angle bisector of this. So, let P n be the angle bisector of angle F 1 P F 2. And what we have to show is that we need to show that this is the normal. So, we need to show that P n is normal to the ellipse. So, since we have taken this angle bisector, let us call these angles to be theta. Now, let us look at the line which is perpendicular to this P n. Then this angle is pi by 2 minus theta, this is also pi by 2 minus theta. So, consider the line passing through P, which is perpendicular to P n. So, proving that P n is normal is equivalent to proving that this line is tangent. So, we will show that this line is tangent to the ellipse. Which means that we have to show that if there is any other point q on this line, then q must not lie on the ellipse. So, take a point q on this perpendicular line, let me draw the picture again. This is the point P, this is N. This is F 1 and F 2. Now, suppose the equation of the ellipse is x square by a square plus y square by b square equal to 1. Then consider a point lying on this line f 2 p, which is at distance 2a from the focus f 2. So, this distance p l is 2 times a. So, consider the point L on the line f 2 p such that the distance f 2 L, this is equal to 2 a. Now, we take any point q on this line, we have to prove that this q lies outside the ellipse. So, this distance is 2 a. What is the so now notice this 2 a is equal to distance of L to f 2, which is less than the distance of q f 2 plus q L. So, if I join this point q to f 2 and L, this is just the sum of two sides of a triangle. Is greater than the third side. So, q f 2 plus q L is strictly bigger than the distance L f 2, which is 2 a. But what can I say about okay, let us look at this q f 1. So, note that since P n bisects angle f 1 P f 2, we get that P q bisects angle f 1 P L. This is because this is perpendicular line. So, if you want to see this, if this angle is theta and this angle is also theta. So, this angle is pi by 2 minus theta, this is also pi by 2 minus theta, and therefore, this angle is again pi by 2 minus theta. So, these two angles are equal. So, we see that P q is the bisector of angle f 1 P L, and therefore, these two triangles are congruent, and therefore, q L is equal to q f 1. So, therefore, q L is equal to q f 1. So, what does this imply? This implies 2 a is strictly less than q f 2 plus q f 1. Now, recall that the ellipse is such that for any point on the ellipse, the sum of the distance from the two foci is equal to 2 a. Because here the sum of the distance is greater than 2 a, this implies q lies outside the ellipse. And hence we have proven that this P n is normal to the ellipse. Okay. Next problem. Need to find the locus of the foot of perpendicular from the foci of an ellipse to the tangents. So, suppose we have consider the ellipse in the standard form x square by a square plus y square by b square equal to 1 with a greater than b. So, we have this ellipse. Now, what we have required to do, suppose I take any general tangent to the ellipse, and then if you look at the to foci f1 and f2, you can draw perpendicular to the tangent from the foci f1 and f2, then we have to find the locus of all such points. So, we know that the equation of tangent, so recall that the equation of tangent whose slope is m is given by y equal to m x plus c, where c square is a square m square plus b square. So, for any fixed value of m, there are two tangents, that is y is equal to m x plus or minus square root of a square m square plus b square. This gives us the equation of the tangent for different values of m. Now, if we have to find, suppose this is any general point h k is the foot of perpendicular, then the equation, so if h comma k is the foot of perpendicular, from foci plus minus a e 0, then the slope of line joining h k to foci is minus 1 by m, because this is perpendicular to the tangent line, and therefore, the equation would be k minus 0 equal to minus 1 by m times x minus or plus a e. This implies m k plus x, x is h, sorry, m k plus h square is equal to a square e square. This is one equation. Also, h comma k lies on the tangent line, therefore, we had equation of tangent line is this. So, k minus m h square is equal to a square m square plus b square. This is equation 2. If we add 1 and 2, then we get m square k square plus h square plus 2 m h k plus k square plus m square h square minus 2 m h k equal to a square e square plus a square m square plus b square. So, we see that this cancels here, this will imply 1 plus m square is common and we get h square plus k square equal to a square. What is e square? E square is 1 minus b square by a square plus a square m square plus b square. So, this is equal to a square minus b square plus a square m square plus b square. B square cancels and this is equal to a square times 1 plus m square. So, 1 plus m square can be cancelled and this gives h square plus k square equal to a square. Since this is true for any h comma k which is foot of the perpendicular, therefore, the locus is x square plus y square equal to a square. So, in this picture this h comma k lies on circle of radius a centered at the center of the ellipse. So, this is called auxiliary circle. So, the foot of the locus of the foot of perpendicular from foci to tangent is the auxiliary circle of the ellipse. Okay. Next problem, we want to determine what is the maximum possible area of a triangle inscribed in an ellipse. So, to solve this problem, let us use the parameter for a general point on the ellipse. So, let a equal to, so a cos theta, b sin theta, b equal to a cos phi, b sin phi, c equal to a cos psi, b sin psi, b any 3 points on the ellipse x square by a square plus y square by b square equal to 1. So, we are considering any 3 points on the ellipse where theta, phi and psi are the eccentric angles. So, that is theta, phi, psi are the eccentric angles of the points. So, we saw in the last class that if we have this ellipse and if we take any point here A, B and C, then this eccentric angle is nothing but if I look at the auxiliary circle, then we look at the corresponding points on the auxiliary circle. So, let us look at this point P, this point Q, and corresponding to C there is a point, this is C and this is point is R. So, this theta, phi and psi are actually the angle of the point P. So, P is the point A cos theta, B sin theta, sorry A cos theta, A sin theta. So, let me write it in the next page. So, let P equal to A cos theta, A sin theta, Q equal to A cos phi, A sin phi, and R equal to A cos psi, A sin psi, be the corresponding points on the auxiliary circle x square plus y square equal to a square. Now, recall if we have the coordinates of any 3 points as x 1 y 1, x 2 y 2 and x 3 y 3, then area of triangle whose vertices are x 1 y 1, x 2 y 2, x 3 y 3 is half of, we look at determinant of x 1 y 1 1, x 2 y 2 1 and x 3 y 3 1, and the absolute value of this gives the area of the triangle. So, we will use this formula. Therefore, area of triangle ABC is equal to half times, we look at the determinant of x 1 is A cos theta, x 2 is y 1 is B sin theta 1, A cos phi, B sin phi 1 and A cos psi, B sin psi 1. This is equal to half A is common from the first column and B is common from the second column. So, half A B times cos theta sin theta 1 cos phi sin phi 1 and cos psi sin psi 1. Also, what is area of triangle PQR, where now PQR are points on the auxiliary circle of radius A. So, here the difference is only the y coordinates are, now instead of B sin theta I have A sin theta. Similarly, A cos phi, A sin phi 1, A cos psi, A sin psi and 1. This is equal to half A square times cos theta sin theta 1 cos phi sin phi 1 and cos psi sin psi 1. So, this is same here. So, what we see is that therefore, area of triangle ABC by area of triangle PQR is equal to, if I divide these two, I get this ratio is B by A. So, we see that area of any triangle inscribed on the ellipse is of constant ratio B by A to the area of the corresponding triangle PQR on the auxiliary circle. Therefore, area of triangle ABC is equal to B by A times area of triangle PQR. Now, this PQR is a triangle inscribed in a circle of radius A. So, we know when this has maximum area. So, again recall this fact. Triangle PQR inscribed inside a circle has maximum area when the triangle is equilateral. So, if I have this circle of radius A and then we want maximum possible area of this triangle PQR, this happens exactly when this triangle is equilateral triangle. So, if we have this PQR, this is the center of the circle, we are taking this radius to be equal to A, and therefore, we can find what is the maximum possible area of this equilateral triangle, because if you look at this angle is pi by 6. So, this is the side length will be 2 times A cos pi by 6, which is equal to 2 A into root 3 by 2, root 3 times A. So, if A is the radius of this circle, then the side length q r is root 3 times A, and therefore, maximum area of triangle PQR is equal to root 3 by 4 times side length square root 3 A square, which is equal to, this will be 3 root 3 by 4 A square. And hence, maximum area of triangle ABC will be B by A times this 3 root 3 by 4 A square, which is equal to 3 root 3 by 4 times AB. So, this is the maximum possible area of a triangle inscribed in an ellipse. Okay, so, this brings us to the end of this lecture. In the next lecture, we will do some problems on hyperbola and rectangular hyperbola. Thank you.